topic that will be covered in this video is Ethernet. More specifically, I will discuss its purpose, the topology of an Ethernet network, and the CSMA/CD protocol. Here are the sources I used to create this video. Ethernet is a popular network protocol that allows users within geographic proximity to transmit data to each other at relatively high speeds, meaning anywhere from 100 megabits per second up to 10 gigabits per second. In other words, it is used to implement efficient local area networks. Ethernet is connectionless, meaning that it sends data without any setup or acknowledgements from the destination host. Although this approach is more efficient than connection-based protocols, it is also less reliable than them. The Ethernet protocol operates within both the physical layer and the data link layer in the OSI model. The physical portion of the protocol dictates what hardware should be used within the network. On the other hand, the data link portion of the aforementioned protocol can be described as the union of two parts: the media access control, or MAC sublayer, and the logical link control, or LLC sublayer. In order to better illustrate the purpose of these two sublayers, let us first talk about the structure of messages sent on Ethernet networks. Messages on an Ethernet network are transmitted using packets known as Ethernet frames. Each frame is made up of four parts: the preamble, the header, the data, and the frame check sequence. The preamble is a sequence of bits that indicates the beginning of an Ethernet frame. It essentially enables hosts to differentiate between random noise on the network and meaningful data. Immediately after the preamble comes the header. Three important fields are specified here. Now, we need to take a slight detour to explain the significance of the data contained within these fields. In order to connect to a network, each end host must have a device known as a network interface card. Each of these devices has a unique hardware number, which is used by the MAC sublayer to identify and differentiate between hosts. This number is known as a MAC address. It is a 48-bit value. The first bit in the address indicates if the address is a unicast address or a multicast address. The second bit indicates if the address is assigned by the vendor, making it universally unique, or by a local system administrator. If the address is set by the vendor, then the next 22 bits identify the manufacturer of the network interface card, and the final 24 bits indicate a unique value assigned by the aforementioned manufacturer. Going back to the Ethernet frame header, the first two fields of said header are both MAC addresses. The first field contains the MAC address of the intended recipient of the given frame. This allows an end host to determine if the given Ethernet frame was intended for them. The second field is the source MAC address of an Ethernet frame. Unlike the first two fields, the third and final field is dealt with by the LLC sublayer. The LLC sublayer serves as an interface between the link layer and higher level layers such as the network layer. To accommodate the functions provided by this sublayer, each Ethernet frame must specify which upper layer protocol should be used with the given frame. Such information is given in the ether type field. Following the header comes the data, which can range anywhere from 46 to 1500 bytes. Depending on the Ethernet standard used, for example Ethernet 802.2, the data may be further encapsulated within an LLC packet, whose header contains data used to establish paths, which in turn would be used by upper layer protocols. After all that comes the frame check sequence. This value is used to verify the integrity of the frame via a cyclic redundancy check. Now that we know the structure of an Ethernet frame, let us examine how these frames get from their source to their intended destination in an Ethernet network. This first requires us to discuss the topology of said networks. There are only two types of topologies used to implement Ethernet networks: the bus topology and the star topology. First, let us discuss the bus topology. Here, end hosts communicate with each other through a single shared backbone cable known as a medium. This unit, composed of a set of devices connected by a single wire, is known as a segment. Since all hosts are connected to this aforementioned medium, every message sent on it would arrive at every single host on the segment. However, as mentioned earlier, hosts will typically ignore Ethernet frames if they are not addressed to them. A single cable can transmit at most one message at a time. As a result, if two hosts decide to send a message on the same cable and at the same time, a collision will occur and all of the data sent will be lost and garbled. An area of a network in which such collisions can occur is known as a collision domain. Due to the fact that all hosts on an Ethernet segment are using the same cable for communication, each segment makes up one large collision domain. As a consequence of this, as the number of hosts on a single segment increases, so does the probability that data collisions will occur. And as collision frequency increases, less data will be getting to its destination within a timely manner. So as it stands, the bus topology scales very poorly. One way to deal with this congestion issue is to fragment a busy network into a bunch of different segments which are connected together via devices known as bridges. These devices build forwarding tables based off of network activity, so it can detect which messages require inter-segment communication. In other words, it only sends messages between segments when necessary. Notice that this means that every message will not necessarily reach every host on the network. As a result, hosts sending messages at the same time does not necessarily result in collisions. Thus, bridges effectively reduce the size of collision domains by isolating parts of the network. This allows for more messages to be sent at a given time and decreases the probability of collisions. Although Ethernet networks can be implemented with a bus topology and bridges, nowadays people prefer the use of the star topology and switches. In a star topology, every end host is connected to the same central device, which these days is often a switch. Basically, it takes the idea of network segmentation mentioned earlier to an extreme, as this topology effectively isolates every single host on the network. Like bridges, switches build forwarding tables based on the signals it detects. As a result, it is able to transmit any messages it receives directly to its desired recipient. This in turn means that no end host should ever receive frames that are not addressed to them, at least in theory. While this topology greatly reduces the probability of collisions occurring, they are still very likely to happen if hosts just transmit their messages whenever they want to. There needs to be a set of rules in place that dictates how hosts should act so that the network is able to transfer messages reliably, meaning with minimal collisions. Here is where the protocol known as Carrier Sense Multiple Access with Collision Detection, also known as CSMA/CD, comes into play. The Carrier Sense part of the protocol dictates that before transmitting messages, end hosts must check if other hosts within their collision domain are already sending out messages. If so, the host must wait their turn until they detect no activity on the medium. Without the Carrier Sense, hosts will flood the network with their own messages even when the medium is in use, leading to multiple collisions. Here, no messages will arrive at their destination, making the network almost unusable for everyone. Hence, this turn-taking standard allows for multiple access. Finally, the collision detection part of the protocol dictates how hosts on the network can detect data collisions as well as how to react accordingly. The protocol states that hosts must listen to the medium while they are transmitting a message to see if anyone has sent a message at the same time. If so, they know a collision has occurred on the network and they have to retransmit their message. Once a collision has been detected, the sender broadcasts out a jamming signal on the medium to tell all other hosts on the network that a collision has occurred. If both hosts send their message immediately after detecting the collision, they would cause yet another collision. To mitigate this, both hosts wait a random amount of time before attempting to retransmit again. The maximum wait time each host will wait increases exponentially after each failed attempt. Now, let's briefly go over what we have learned. First, we discussed the purpose of the Ethernet protocol, where it fits in the OSI model, and the structure of Ethernet packets. Then, we talked about both bus and star topologies in relation to Ethernet networks. Finally, we covered the CSMA/CD protocol and how it is essential in ensuring an Ethernet network's reliability. That concludes the video. Thank you for watching.